Let's continue with this series of Dmitriy Bilyk, today explaining these energy minimization problems, well, in analysis and discrete geometry. Thank you, Dima.
Okay, thank you very much. Thanks, Ujué. So this is my last lecture. So it will consist of two different parts. So first I'll start on the board, and I want to explain one more problem that I didn't have time for in the first lecture, and it's sort of related to some of the problems from the first lecture, but even if you didn't hear the first lecture, it's completely fine. So this is the problem of so-called mutually orthogonal, mutually unbiased bases. So what are these objects? So assume you have two different orthonormal bases in the d-dimensional complex space. So let's say E and so EI and FJ are two different ONBs in CD. And we say that they're mutually unbiased if you have the following property that for any I and j, the absolute value of the inner product is equal to 1 over square root of d. Okay, so the absolute value is constant for you take two different elements from different bases, and it's easy to see that it has to be 1 over square root of d. And well, these come up in many areas, in many applications, in particular in frame theory, in quantum information theory. Essentially what it says is that, well, if you know the expansion in one basis, you cannot tell too much about the expansion in the other basis. And one very simple example would be you take EIs to be the standard basis, and you take Fj to be the discrete Fourier basis. And so it's easy to see that in this case you'll have this property. And the question is, how many mutually unbiased bases can you have in d dimensions? Okay, so pairwise unbiased. Okay, and there is a very well-known upper bound. Okay, let me call this number m. Okay, so the number of mutually unbiased bases at most 1 plus d. Okay, and I will get back and actually give you an idea of the proof of this theorem, or almost the proof, modulo some computations. And there is also there are several known constructions that tell you the following, that this can actually be achieved if the dimension is a prime or a prime power, okay, then there exists one plus d mutually unbiased basis in CD. Okay. I will not go into the construction, but yeah, the construction, of course, goes into some arithmetic properties of the direction of the dimension. Basically, what happens is that you try to construct certain orbits of operators that shift your basis and that modulate the basis by roots of unity. And if the dimension is prime, it guarantees that this gives you different bases. Okay, so that's the idea. But the question is, what happens if D is not a prime power? And, yeah.
Is this somehow connected to Chebotarev's theorem? About, like, because the matrix of these forms, when D is prime, Like they have all minors invertible when you're doing some choices.
Right, and essentially this is connected to the Mars matrices also, so that which Stefan brought out yesterday. I'm actually not quite sure about Chebetarev's theorem. That's a good thing to think about. I don't know. Okay, right. So the case when D is not a prime power is completely open. So even the case P equal to 6 is open. So let me tell you a few things that are known. So if D has two different prime power factors, then you can do the following. You can do a tensor product construction in the following way. So say D is P1 to alpha 1, P2 to alpha 2. You can write CD as a tensor products of spaces with these dimensions. You can construct, by this theorem, you can construct mutual orthogonal, mutual unbiased bases here, and you will have this number plus 1. And you can construct the same thing here. There will be more of them here. So take just as many as here and take the tensor product. And that would give you a collection of mutually unbiased bases with this cardinality. P1 is the smaller of the two primes. Okay. So this is easy to show, and in particular in dimension 6, and sorry, this is supposed to be D. Sorry, my bad. Yeah, so in dimension 6, in particular, the smaller factor is 2, so you have 3 MUBs and Dirac constructions. Okay. There was for a while a conjecture that this is actually the correct number, but it was shown that in some dimensions which are squares, you can actually construct more. So in general, this is not true, but there is a conjecture that for 6, 3 MUBs is the maximum that you can get. There were some extensive numerical computation searches for at least 4 MUBs in dimension 6, and they were unsuccessful. So people believe that it should be 3. Okay. But the best upper bound that's known is still this. Okay. So it's an interesting problem. It's a pretty famous problem too. Also, I think has its own Wikipedia page. What I want to do now is give you an idea of the proof of this inequality. In particular, an idea of a proof which is related to energy minimization. So my point here in this series of talks is connecting various problems to energy. So initially, this was proved by Wouters and Fields, I think in the 90s. There were several proofs afterwards, but the proof that I'm going to present, well, not exactly, but it's based on the proof that was given by Kolontzakis, Matolci, so two of Ilona's collaborators, and Weiner. So the argument I'll present is a little bit easier, but it's essentially their proof. And the proof is actually very simple. Let's consider this energy, which we have already seen. So if you take n points on the unit sphere in the complex space, we consider this energy with the force power here. We have seen this in relation to the problem of maximal number of equiangular lines. Okay. And actually, these problems are in certain sense dual. I don't want to go into this. We know that this energy, if you view the integral energy, it's minimized by the uniform measure sphere, because essentially you get a positive definite kernel. So this is bounded by the energy of with this kernel, x, with respect to sigma. Okay, and you can compute this quantity precisely. And if you don't want to compute, if you don't want to do calculus, you can recall that we already know that equiangular lines achieve this bound, and then for equiangular lines you can compute it directly. It's simple arithmetic because we know all the parameters. Okay, so you get a certain value, and now assume there exists MUBs. Well, this quantity is super easy to compute. Okay, and if you compute it and write this inequality, solve it, it will give you that m is less than 1 plus d. Okay, so that's this is essentially the proof of Kolantzakis, Matolchi, and Wiener, but just a little bit distilled. Okay. Actually, you could also do the same thing in the real case. In the real case, you would get 1 plus d over 2. And I know this was known before. There is a paper where this is proved in a different way, but I don't think there has been a lot of work about MUBs in the real case. So at least I wasn't able to find too many papers in this, so I cannot tell you more what happens here. But in the complex case, yeah, dimension 6 is already a very interesting open problem. The conjecture is that 3 is the maximum that you can get. Okay. And there is this very nice relation to energy. And actually, so what I just want to emphasize here, this is a certain way of proving non-existence of certain geometric objects. If you have a certain energy, if you find the proper kernel, you would, and you know what the energy is minimized by, so you know the minimal value here, then by doing that, you can prove that certain objects, say if m is greater than number, these objects cannot exist. Okay. Any questions? Yeah. Well, 1 plus d, I guess, is the only thing that. Oh, for the composite case. Well, there's this lower bound, and I don't think there's anything really better than that. I don't think I haven't seen any papers with asymptotic bounds. So there is this lower bound, and again, as I said, for a while it was a conjecture that this should be correct, but that has been disproved. Okay, for some square dimensions, you can have more than this. Okay.
And then other specific, I mean, you said 6 is, all these are open, like things that are not round.
Yeah, whenever d is, so this is open. I don't think in any of those dimensions you haven't, you know the answer exactly. There might be some lower bounds. But yeah. Okay, so I'll leave this and that. It's a good problem. So if you have any ideas, if you solve it, this would be great. Even just dimension 6. Okay, and now I move to the slides, and I want to talk about yet another problem that comes from discrete geometry approximation theory, where energy also plays an important role. So this problem it has already been mentioned by Ujué in the talk. This is the problem of discrepancy theory. So, and here we're going to consider discrepancy on the sphere. Okay, well, discrepancy theory is a pretty broad subject, so you can consider discrepancy in many geometrical settings. Basically, the goal is that you measure how close, how well distributed point distributions are, how close they are to the uniform distribution. And there are many ways to measure it, so one of them is discrepancy. So what we're doing here is the following. So we're on the sphere, we consider spherical caps. So basically a spherical cap is just that you take the sphere, choose a point x on the sphere, and then you cut the sphere at level t by hyperplane. Right? So that's exactly what you think it is. Now, if you have some discrete set of points, you look at the proportion of, for every spherical cap, you look at the proportion of points that fall into the spherical cap minus the size of the spherical cap. And again, I remind you that sigma is the normalized uniform measure. So you hope for this to be small. And then you measure the average. Of course, normally you're interested in the supremum. We've seen this in Ujué's talk before. But L2, if you replace so the supremum with L2, that opens the door for lots of different arguments, in particular, of course, the Fourier analysis. But also, well, sometimes you can just square things out and things work nice. Okay, okay, so this is the L2 spherical cap discrepancy. So you compute the discrepancy for every cap, and then you integrate over all all different caps, all centers and all heights. Okay, then you ask how small can this quantity be, and there is a certain lower bound that was proved by Beck, and actually a big part of today's lectures I will give you a new proof of this fact. So the proof says that this is at least of the order n to the negative 1/2 minus 1 over 2d. So notice that this is actually better than random. So standard Monte Carlo arguments give you 1 over square root of n. Okay, so in here you have this little correction. Okay. Of course, you have to pay the price that you also have the constant in front, which depends on the dimension. But if you're just interested in asymptotics as n goes to infinity, this is a little bit better. It's known also that this bound is sharp. I will talk about this in just a few minutes. So you can construct, at least implicitly, at least probabilistically, you can construct collections of points which would achieve this bound. Well, there is one very important connection of this object to energy, okay? And this is an identity which was discovered by Stolarsky in the 70s, and it's known as Stolarsky identity or Stolarsky invariance principle. It tells you that up to a certain constant, the L2 spherical cap discrepancy squared is equal to the difference between the continuous and discrete energies where the kernel is just the Euclidean distance to the first power. So this Rees energy with parameter s equal to -1. So this is actually an identity. It's not some asymptotic relation. This is an exact identity, which is, the first time I saw it many years ago, I did not quite believe it. But then I did not believe it to such an extent that in the end I came up with a new proof of this, which is quite simple. So there were several proofs of this fact. Yeah, so I think the paper by Brauchert and Dick was called a simple proof of the Stolarsky identity. And then I wanted to write a paper called an even simpler proof of the Stolarsky identity, but in the end that just got incorporated into a bigger paper. And the main idea is the following. Well, let's go back for a moment and let's look at the formula for discrepancies. I can replace this number by the sum of indicator functions, right? Okay, and if you square things out, the sum of indicator functions becomes a double sum. That's where you get the energy, right? So when you get that energy, when you start integrating, when you integrate in x, essentially you would get the area, the size of the intersection of two spherical caps. Right. So you integrate the product of characteristic functions, you get the intersection. You can compute it. There are formulas for this thing. They're pretty ugly. So there are some easy things you can say, of course, if xi and xj are far away, this is 0, right? But in general, you don't get a nice looking formula. But if you now integrate this in t, as it often does in analysis, this becomes much nicer. And this is a computation that you could give in your calculus class, well, maybe with some appropriate hints. In this case, this is just equal to 1 minus a constant times the Euclidean distance minus the points. Okay, and then essentially the rest follows. There is some stuff to do, but okay. So this is a very nice relation which provides you with this identity. Okay, so this identity basically tells you that minimizing the L2 discrepancy is exactly the same as maximizing the sum of distances. Okay, it has it's been a pretty active area of research in the last few years. There are various versions of this identity in various geometric settings, on projective spaces, for different distances, on general metric spaces. I want to mention one case, the hemisphere discrepancy. So if you replace, so basically instead of integrating over t, you take the median with respect to t. So you take t equal to 0. When t equal to 0, these are hemispheres. And understanding the size of the intersection of two hemispheres is very easy. It depends linearly on the angle, right? So the angle is the geodesic distance. So then in that case, you automatically get the same, almost the same identity, but with the geodesic distance. Okay, and this was noticed simultaneously and independently in the same year by Skriganov and by myself with Feng Dai and Ryan Metzger. Okay. All right, there are also some very simple consequences from this identity. You can, in particular, some of the things that would have been harder to compute for discrepancy become almost trivial to compute in this case. For example, if you compute the expected value of the discrepancy of random points, it becomes very simple here because by linearity of expectation. Also, you could prove, this way it becomes very easy to prove the sharpness of Beck's estimate. So for this, you use something that's called jittered sampling. Let me explain what that is. I'll do this on the board. So that's a way of constructing random distributions which perform better than IID random points. So you take the sphere and you divide it into pieces. So you take a so-called regular equal area partition. Okay, where all pieces have exactly the same area. Okay, and their diameter is roughly the same as if these pieces were actually balls. So this would be n to the -1/d. Okay. So the pieces roughly all look the same and roughly all look like balls. Okay, and then you choose one random point independently, uniformly in each piece. Okay. And then it's very easy to compute the discrepancy of this if you use the Stolarsky representation. So in the second part, in the sum, when you take the expectation, the diagonal terms would go away. They would give you 0. But the non-diagonal terms would actually give you the integral over a pair of these subdomains, say i's and j's subdomain. Okay. So if you put it all together, you get almost the integral over sphere across a sphere, except for these diagonal parts. And on the diagonal parts, you can estimate it very simply using these properties. Okay. And from this you get sharpness. So notice that this is the square. So if you take square root, that's n to the -1/2 minus 1/2d. That exactly matches Beck's lower bound. Okay. Also, another thing that comes out of this identity for free is that this quantity, this sum, is always bounded above by the integral with respect to the uniform measure. Okay. There are other ways to prove it, but here it's just for free because this is a non-negative quantity. Okay, you can now take the limit as n goes to infinity, and so you can approximate any measure by discrete measures, and you have the same for measures. So basically, this gives you one possible proof of the fact that this function, this kernel, is negative definite, conditionally negative definite. So it's maximized by sigma, not minimized. Okay. All right. So what I want to do next is I will actually give you a new proof of Beck's lower bound. There have been at least a couple proofs before. So the original proof due to Beck, if I remember correctly, was based on Fourier transform methods. There was also a proof by myself and Feng Dai based on spherical harmonics and Gegenbauer polynomials. So the proof that I'm going to present now takes all of that out of the picture, and I don't know how appropriate it is for this conference, which is called Fourier Analysis and Beyond. I'm taking all of the Fourier analysis out of the proof. Okay, so let's say I'm going beyond. Yeah, okay. All right, so let's start. Okay, we have this kernel, which is the Euclidean distance. If you remember, we usually wrote things in terms of the inner product, so that's square root of 2 times 1 minus the inner product, square root. Okay, so our function that we're interested in is square root of 1 minus t. Write the Taylor series. Okay, if you compute the Taylor coefficients, they're all negative. Okay, and we know now if you flip the signs that this gives you a positive definite kernel, right? Okay. Well, you can compute those coefficients, and you even know the behavior. The behavior is m to the negative 3/2, which is nice because that makes the series converge up to the endpoint, so you don't care about interchanging sums and integrals. Okay. All right. Yeah. So we write our kernel in this way, and then we plug it into the Stolarski identity. Okay. And what you get is. Well, you get this relation where I already interchanged the sum and the integral. Okay. Right. The coefficients are now positive because we're subtracting in the opposite way. So now the coefficients become positive, and the term which is m equal to 0 cancels out because that term is exactly equal to the integral. Okay. All right. Any questions? So I'm actually doing pretty much the full proof in about 10 minutes. Okay, all right, so I just rewrite it here. So we know we can compute this integral. We know what it behaves like. So of course it's 0 if m is odd, okay, and it's non-zero if m is even, but it's quite easy to compute it. It's a calculus exercise, okay. And now we'll look at this difference. And the question is this difference positive? Well, this is what we were doing in the first lecture. This difference is positive. Okay, let me very briefly remind you. So this is a copy from the previous lectures. This slide actually propagated into all 3 lectures. Okay, so we discussed this. So you get, because this kernel is positive definite, the energy is minimized by the uniform measure. So the minimal value of the energy, the lower bound, is the integral with respect to the sigma. Okay. All right. Okay. And that means that if we look at this expression, everything is positive, and if we want a lower bound, we can throw away as many terms as we want. Okay. So this is what we're going to do. Okay. Feel free to stop me if there are any questions. Okay. Okay. So. What I'm going to do is the following. I'll throw away all the odd terms. They're positive, but there are things here which are positive and negative, so this would be hard to work with them. But altogether, the whole thing is positive. I can throw it away. So I only leave the even terms. Also, with the even terms, I'll throw away an initial chunk. Okay, so I'll throw away all the even terms with small powers. Okay, to be determined in a moment. Okay. And then I will also, in those even terms that are left, I will throw away all of the off-diagonal terms. And it seems that this is lossy as hell, that there is no way that this can give you a sharp bound, but it turns out that it does, and it actually, if you're a little careful, it gives you very sharp bound, well, very close to a sharp bound. Okay, so let's see how things work. All right, so okay, I've only left the even terms. I only start from some m large enough. I know this guy. Let's look at what happens here. So now, since I have even terms, everything here is positive, so I can throw away whatever I want. I throw away all the off-diagonal terms. The terms on the diagonal are all equal to 1, okay, and there are n of them, so here I get 1 over n. Okay. This number here is at most some constant times m to the minus d over 2. Okay, so I can lower bound it this way. Now, if I take m large enough, it's of the order n to the 2 over d with some constant in front, I can make this less than 1 over 2n, so that the whole difference will be at least 1 over 2n. Okay. Any questions? All clear? All right. And then, well, and then we're done. You just pull out 1 over n. This is m to the negative 1/2, this series here, and you plug in what you chose for m, and you get the bound. That's it. So that's the whole proof. Again, as I just said, it seems that this proof loses a lot. But it turns out that it really doesn't, which, to be honest, I don't completely understand yet, but there are some indications why it doesn't. In particular, let's look at the part where we threw away, well, first of all, we threw away the odd terms. Well, all the odd terms could actually be 0, because if your set is symmetric, if you choose a symmetric set, odd terms will give you 0. Okay? Both the sum and the integral will be 0. Okay, then we threw away even terms, a number of even terms. Oh, by the way, this proof is actually strange, because if you remember your calculus classes, if you worked with Taylor series and you want to estimate something using Taylor series, you usually use the initial chunk of the Taylor series and throw away the error. We're doing the opposite here. We're throwing away the initial chunk and estimating things by the error term, in a sense. Okay, so you're throwing away many initial even terms. Could they be 0? Well, what would it mean? It would mean that this expression would have to be equal to the integral. Well, that's almost the definition of spherical design, right? So, well, when do spherical designs exist? And this is, again, a copy of the slide that I had in the previous lecture. So we know that from the result of Bondarenko, Radchenko, and Vyazovska that spherical designs of the order m to the d, spherical m designs of the order m to the d exist. Okay? So that means that m is roughly n to the power 1 over d. So going back here up to the power n to the 1 over d, you know that these terms actually could be exactly 0 if you took a spherical design. Well, we're going higher. We're going to n to the 2 over d, and we haven't explored it too much, but I suspect that maybe you can prove that up to this order you have things that are approximately spherical designs that give you a fairly small error. So this can probably be worked out. Okay, so it does. The proof does lose a lot, but turns out that not so much. Moreover, in this proof, if you do it a little bit more carefully, so maybe not as carelessly as the way I did it here, you run the computations with a few more details and with watching the constant, and this is definitely Johann Brauchert's. By the way, yeah, this argument is our joint work with Johann Brauchert from last year. So you watch the constants, and this is where Johann comes in, because I think he has Mathematica in his head. I think he just speaks in hypergeometric functions and stuff like that. And then you can try to see which constants you get out of it, and there are actually conjectured values of the constant, at least in dimensions 2, 4, 8, and 24, and probably by now many of you recognize what those dimensions are. So those are dimensions where you know something about sphere packing, where you have some very special lattices, and the conjectured values of the constants, they were actually conjectured by Brauchert, Hardin, and Saf. They come from the conjectures in the Euclidean space for the best packing, and the idea is that the best distribution of the sphere have to locally look like those lattices in the Euclidean space. Okay. And then if you translate those constants to the sphere, that's what you get. And surprisingly, if you run our argument a little bit more carefully, you get very close to the conjectured constants. Okay, so in dimension on S2, that's just within 3% of the conjectured constant. So it's I'm quite baffled because that this argument gives you such a sharp estimate. It gets you so close to the conjecture. Okay, and then the next few minutes, I want to give some more applications of the method and some generalizations. One application is the following. Yeah.
So, dimension 3, does it make sense?
Well, I think there is a general conjecture, but let me see. Right, yeah, I'm missing dimension 3. Let me see, I would need to look at the paper, I don't remember. Well, this might be a typo. That might be dimension 3, actually. Yeah. Yeah, sorry. I think it's actually dimension 3. Yeah, thank you. Yeah, so let's go back to the method. It turns out that since this method is so simple, it gives you lots of new results and also generalizations. So in terms of new results, you can do the following. You can look at this expansion, and you can say, well, we can, since all the terms are positive, we can just throw away whatever we want, and we can leave just one term, and we can estimate what's left by, we can estimate the discrepancy by just one term with any given m. Let's take m equal to 1. Okay. Well, when m is equal to 1, this will go away. You will just have this sum, and this sum is just the square of the sum of the vectors, right? And that gives you this inequality. The discrepancy is bounded by the norm of the center of mass. Okay. Which, if you think about this heuristically, this makes a lot of sense. So this tells you that if the set is very unbalanced, then discrepancy has to be large. It cannot be well distributed. Okay. However, even though this is very, very natural, I've searched in the literature quite carefully, and I haven't found any statements of this form in the past. Okay. So the discrepancy is bounded below by the center of mass of the points. Okay. You can also, if you take m equal to 2, for example, then you get the object that we discussed a lot in the first lecture. You get the frame energy. Oops, sorry. So the sum of squares of inner products. Right, and this tells you, in a certain sense, if the set is too far from being a tight frame, then again the discrepancy has to be large. Okay, and again I haven't seen such properties. You can take other terms and you can sort of interpret it in terms of spherical designs. You can say that if a set is too far from being a spherical design, then you have some lower bound for the discrepancy. All right, and finally, so maybe I'll finish a little early today. Okay, well, I want to talk about some generalizations that come in from this method for free. So, for example, if you take other values of alpha in these Reese energies, so still positive values, you can look at this difference, and there is an analog of Beck's bound. It's known that the lower bound, that it's a sharp lower bound, which you can also prove using jitter sampling, is -1 to the n to the -1 minus alpha over d. Okay. This was proved by Wagner in the 90s. And the proof is actually, it uses spherical harmonics and Gegenbauer polynomials, and it's quite technical. It's actually, the paper is short, but quite hard to read. Okay. Here you can just plug this kernel into, take its expansion, and run the same argument that you would get it in a few lines. Okay. So this, you can generalize it also to other kernels. So if you have a kernel that's analytic and that has this expansion which converges up to the endpoints, and where the coefficients are of this order, okay, then you can get this lower bound without having any geometric information about the kernel, but only knowing the information about the expansion. Moreover, you can even go a little bit further. You can say, okay, let's have a kernel where we know that things converge uniformly, but we have this order estimate only for the even terms. Remember, in the argument, we don't care about the odd terms because we throw them away anyway. So if you have this estimate just for the even terms and the odd terms are different, that still works and you get this bound. Okay. And finally, I want to mention one more result, one more generalization that comes out of this argument is, this is the following. Well, discrepancy, what it does, it approximates the uniform measure by point sets, so essentially by zero-dimensional sets. You can ask a more general question. What if we try to approximate the uniform measure by sets of a given Hausdorff dimension on the sphere? Okay, something between 0 and d. Okay, so in this argument, the only property of such sets that we would need is certain regularity. In particular, we would need them to be lower Alfors-David regular. So, by the way, just a little funny story. So very often in the geometric measure theory community, you will see this abbreviation ADR, which stands for Alfors-David regular. Guy David actually hates this. He says that it should be called Alfors regular, but everybody still keeps calling it Alfors-David regular. Yeah. So what it means is the following, that if you take any point in your set and take an epsilon ball around that point and take the intersection, the S-dimensional Hausdorff measure is at least of the order epsilon to the S. So the set is at least S-dimensional at every point. Okay? So there is some sort of uniformity. So you cannot have, like say if S is equal to 2, you cannot have something like this, because then it's one-dimensional here and it's two-dimensional here. So this would be lower Alfors-David regular with S equal to 1. Okay. All right. If you run the same argument, you can do almost everything almost exactly, almost verbatim the same. The only difference is you cannot leave just the diagonal terms, right? It's not a sum anymore, it's the integral. But you can replace the diagonal terms by the integral over points which are epsilon close. And then you can play around with that epsilon and just optimize an epsilon. And then the bound that you get is the following. So here notice this the S-dimensional Hausdorff measure of your set X with which you're trying to approximate the uniform measure. This plays the role of n. Okay? So in the case of S equal to 0, you have n points. The Hausdorff measure is just the counting measure, so that would be n. Okay? And you get a certain power depending on D and S. We unfortunately were not able to prove yet that this is sharp. We believe that this might actually be sharp. One part of this belief comes from examining the endpoint cases. So if you, well, first of all, it gives you the same, for S equal to 0, it gives you the same as what we already know for endpoints. Right? So you get this. As S goes to D, this becomes minus infinity, which makes sense for if you want to approximate the uniform measure by D-dimensional sets, you can just take the uniform measure, right? So you get, there is no lower bound that you expect. Okay, an interesting subcase of this theorem is when you take S equal to 1 and you consider lines. So if you consider rectifiable curves, closed curves, or non-closed curves with sufficiently large lengths, they will automatically be lower Alfors-David regular with a constant, something like 2, because for every small ball the curve has to go in and out. And then you get this lower bound on the estimates on the approximate discrepancy with spherical cap discrepancy with respect to lines instead of points. Okay, so L is the length of the curve, and this is the power that you get. Okay, and again, this would be very interesting to see whether this is actually sharp. Okay, and we don't know yet, but we suspect that yes. And I finished a few minutes early, so I'll stop here.